Okay, so I'm going to do an example. If we are given two lines in vector form, so let's say we have, 7 minus 2t minus 4 plus 6t minus 6 plus 8t. So we know that these are lines because they only have one free variable or one vector. These are in vector form because they're in the bracket. Whoops. Okay. So I've got two lines here. These are in vector form. I could write them in parametric form. So the first one would be 7 minus 2t is the x component, y is minus 4 plus 6t, and z is minus 6 plus 8t. And then this is your first line. Oops. They called it r of t. And our second line, r of r, is x component minus 6 plus 5r. Y is 15 minus 5r, and z is 4 plus r. So here's two lines. And if we wanted to know if there is a point where they intersect, so say, for example, find the intersection. So to do that, we would want to find a t and an r that we could plug in that would give the same point, x, y, and z. Right? If they both went through the point 0, 0, 0, then that would be the intersection point. So we need to find a t and an r so that that will work. Okay, so how do we do that? Well, equal. If we want the equal. Now, this, but let me rearrange it a little bit. Let's say 5r plus 2t, so 13 equals 5r plus 2t. This is an equation, a linear equation with two variables. So if we could find the r and the t that would make that we could plug in to make this equal to 13, then that would be where the x values are equal. Now, these are the x values. What about the y values? And then let's rearrange this in the same way. Let's change all the signs here. So if we said 5r plus 6t equals 19, and let's rearrange this one, 5r plus 2t equals 13. So we've got two equations here. If I could find an r and a t that worked in both, and we could try it out in the z as well. So you would also want the z components to be equal. And if they didn't work, they would have to be the same r and t, because you can only plug one r in here and one t in here, and it would give you the same point. So let's say 8 t minus r equals 4 plus 6. And if I just put this in the same form as the other ones, the r first. I just put the r's first in the others. So we could solve for one and plug it into the other. We could set them up and do elimination, however it is that you solve an equation. So let's just line the first two up. 5r plus 6t equals 19. If I subtract this equation from the other, so if I had minus 5r minus 2t equals minus 13, and I added that to 5r plus 6t equals 19, this is called elimination because I'm eliminating the r's. This will be 4t equals 19 minus 13 is 6. 2 I get for the t value. T value into either one r plus 2t. 5r plus 2 times 3 over 2 equals 13. So what I found is an r value of 2 and a t value of 3 over 2 that would make the x and the y work. So what were the x component of the first one and the x component of the second one, the second line? So I'm saying if I plugged this in, 7 minus 2 times 3 over 2, I get 7 minus 3, which is 4. And if I plug the r into the second one, I get minus 6 plus 10, which is 4. So the x values work. Now what about the x value in the, oh no, sorry, the y values? So the y components were minus 4 plus 6t, and the y component was 15 minus 5r. So if I plug the t in, 6 times 3 over 2, get minus 4 plus 3 is 18 divided by 2 is 9 is 5. 5 times r is 2, so 15 minus 10 is 5. So that works. Now what about the z component? So z is, now I didn't use this equation finding them, but it would still have to work with that same t and the same r for there to be an intersection point. So z is minus 6 plus 8 and t is 3 over 2. Is 6. 4 plus r is 6, and so they work. So we found the t is 3 over 2 and r is 2 gives the intersection point as the point 4, 5, 6. Now, if you found that t and that r and they worked in the first one and the second one, the x and the y, but they didn't work in the z, then we would say there's no intersection point. But the question on the homework actually says find the intersection point, so you know that there is an intersection point that works.